Right. It looks like I'm being recorded here, so I didn't get the countdown. I don't know what's going on there. I've already made the answer key to this here review sheet. So I just want to quick kind of guide you through that here. So you go here. All right. Review sheet solutions. So let me try to use this pen here, maybe as like a little bit of a highlighter. So this one we had already done, but let's talk our way through this. So the main things you're going to have to do for this test are, energy bar diagrams, which we did a ton of those examples. Conservation of energy, which is what this is. Work, and then possibly a little bit of power as well. So hold on a second, Fred. So this here, conservation of energy, work, and then power. So going back here, what you got to realize about this setup, or any energy setup, is that the total energy remains constant at any point in the object's motion. So when it all starts out spring energy here, it gets converted into kinetic. Then it gets, as it goes up the hill, it loses some of the kinetic, gets converted into gravitational energy. Then it comes back down the hill. It's going to lose that gravitational, get the kinetic energy back. It's going to go up the hill to here. It's going to be a combination of kinetic and gravitational. Up here, it's still going to be a combination of kinetic and gravitational, but it's going to have more gravitational than it had when it was at this level because it's higher off the ground. Then when it gets all the way back to the bottom, it has all kinetic energy again. So the total energy at any single location here has to be constant. So determine the spring constant of the spring. Well, the whole trick with this is we have to determine the energy up here, right? And then that energy, right? That's this total energy at the top. That has to equal the spring energy at the bottom, which is the energy down here. All right. So you go through PG at the top, KE at the top, add them together, you get about whatever that is, that adds up to the total energy. Well, I forget what that is. I'll have to scroll down in a second here. And then over here, that's the energy stored in the spring at the bottom, right? 1/2 kx squares. K is the unknown. So when you look here, I'm going to go back to the mouse here. The amount of energy stored in the spring is this total here, which is 11,288. I set that equal to 1/2 kx squared. I solve for k. I get 22,600 newtons per meter. Now, determine the velocity of the cart after it's launched. So that's the velocity when the cart's right here. All right. Well, that's the trick. It's all kinetic energy at this point, right? It's literally all kinetic energy. So that 11,280 joules that we calculated here, we don't have to recalculate. We know that that's going to be the total energy at any one of these locations. So since here it's all kinetic energy, then we just set that equal to 1/2 mv squared. That'll be the v of the cart right there. Solve it through, we get 17 meters per second. Determine the speed of the cart at the top of the first hill. So the speed of the cart right here. Well, I have to factor in gravitational energy up there. So mgh plus mv squared. So it's the same total amount of energy, but now it's divided up between gravitational and kinetic. So you go through the math, you get about 5,250 joules of kinetic. You have to subtract that off, of gravitational. That leaves you with only 6,038 joules of kinetic energy equals 1/2 mv squared. Solve for v. V equals 13 meters per second. Great stuff. Now this next question here, this is a work problem, right? 50 Newton force applied to a 5 kilogram object moving with an initial velocity of -20. So it's moving to the left. So its initial kinetic energy has an initial kinetic energy, but it's moving to the left. The force is to the right. So that force, that work that's going to be done by this force is going to take kinetic energy away from this block because it's going against the motion. It's going to slow it down. So the work done is simply equal to force times displacement or change in kinetic energy. I don't know the change in kinetic energy because I don't know the final speed. All right. So what I have to do is find the work done, which is force times distance. 50 newtons times 10 meters, 500 joules, but negative because the displacement and the force are opposite signs. Comes out negative. So that means kinetic energy is taken out of the object by this force. So then the final speed of the object, we know the change in kinetic energy is negative 500 joules. All right, so whatever the initial kinetic energy, it looks like it ends up being 1,000 joules. That's going to get taken away from it. And you go through the math and you find that the final kinetic energy is 500 joules. You don't have to set it up all in one equation, right? You can find the change in kinetic energy. Then you can do this calculation on its own. So you know it starts with 1,000 joules of energy. We said we're going to take away 500. So that means we're going to end with 500 joules of kinetic energy. So the final kinetic energy is 500 joules. Set that equal to 1 half mv squared. Solve for v, 14 meters per second. The last one here, 600 kilogram sports car increases its velocity from 20 to 60 over a distance of 30 meters using work energy concepts to determine the net force to propel the car over this distance. All right, so this is one where you can't just find F delta X because you don't know the force. But since you know the initial and final velocity, you can find the initial and final kinetic energy. So the final kinetic energy, right here, minus the initial kinetic energy, has to equal force times 30 meters. I did a little algebra here to make the calculation simpler. I brought the 1 half 600 out in front. You don't have to. You can just find this, subtract it. You should get 960,000 joules. That's a change in kinetic energy. All right. It's positive because it's increasing. That equals force times distance. So that divided by 30 equals 32,000 newtons. Now, determine the time it took the car to go from 20 to 60 meters per second. We just got to use some kinematics here. Average velocity is displacement over time. The average velocity here is 40 because it's 20 plus 60 divided by 2. So the time is 0.75 seconds. So all we have to do then is power equals change in energy over time. So it's changing by 960,000 joules in 0.75 seconds. So that's 1,280,000 watts. All right. So if I give you a power calculation on this, it'll be something very simple, similar to the lab or something like that. It's a very basic power calculation. I'll probably tell you the change in energy or something, and then ask you to divide it by the time. So again, big things here: work energy, conservation of energy, work, and power. Now, if I'm you, what I do is I go back to some of these solutions, probably worksheet 3. And I look at some of these problems and I say, okay, yeah, this one here, do I know how to do it? This one here, do I know how to do it? Work through these in your head, a couple of these basic problems. I think there's some other ones here too. You can go and look at the worksheet quiz 3 solutions. Okay, which one was that? Oh yeah, this one. That's a good one. It's a little different, I think, than the one I gave in class. But these would be great questions to study for the test here. Really, really great question. These are the 3 main conservation of energy, right? Gravity into kinetic. This one's going from kinetic into gravity. This one's going from kinetic into spring. All right. So take a look at these. Give me some emails tonight. I'll probably answer emails up to about 10 o'clock. I'll talk to you guys later.